Alright, so today we're going to start talking about something called molecular geometry. And what molecular geometry means is that we're looking at the 3D arrangement of how a molecule's atoms look in space. So far we've done Lewis structures, in which kind of gives us a 2D flat picture of what an atom or a molecule might look like. But today we're going to explore the three-dimensional side of that and how these atoms are arranged while floating in space. Okay, so now we've got to start being able to picture things three-dimensionally a little bit. So we're going to talk about some angles. We're going to talk about different shapes that can be possible for certain compounds. Okay, so to start talking about molecular geometry, we have to look at the number and the type of what we call electron domains. Okay, so to help us determine the molecular geometry or the shape around the central atom, we need to look at these something called electron domains. Okay, so what an electron domain is basically telling us how many different groups of things are around the central atom. Okay, so I want to kind of make a distinction here. It doesn't have to necessarily be things bonded to the central atom. It's basically how many things are surrounding the central atom. Okay, it doesn't have to be bonding. They could be lone pairs. Okay, we could be looking at lone pairs around that central atom. So we've got to make a distinction there between what we call bonding domains and non-bonding domains. Okay. So when we're looking at molecular geometry and we're trying to figure out the three-dimensional shape of an object, it's pretty hard to tell just looking at its formula. Okay, if we look at a water molecule or H2O molecule, it doesn't give us a very good indication of what its three-dimensional shape might be. Okay, we know that there's 2 hydrogen atoms and 1 oxygen atom, but it doesn't give us a very clear idea of what it's going to look like three-dimensionally or in real life. So what we have to do is we're going to start looking at a theory called Vesper theory that's going to help us kind of determine how to draw these things three-dimensionally, what shape they're going to take on three-dimensionally, and what they're going to look like floating in real life. All right, so this Vesper theory, or what I call Vesper theory, stands for Valence-Shell Electron-pair Repulsion theory. Okay, that's an important acronym that you need to have in your notes. Okay, you'll need to know what this acronym stands for. Valence-Shell Electron-pair Repulsion theory. So I'm going to kind of break this down a little bit for you. Valence shell, when we say valence, we mean outer electrons, right? Our valence electrons are the ones in our outermost shell available for bonding. Okay, so when we talk about valence, we're looking at our outermost electrons, the ones that are available to bond. Electron pair, we call these lone pairs. Okay, so we've got these outer electrons in lone pairs. And electrons tend to repel each other, right? Because they are both a negatively charged particle. So electron pairs or lone pairs are going to tend to repel each other. And they want to be placed three-dimensionally as far apart as they can. Okay, they want to space themselves as evenly as they can around that central atom so that they have the most space to themselves. Okay? And when we think about electron pairs, I want to make a distinction here also. It's not necessarily lone pairs. It could be a bond also, right? How many electrons are in a chemical bond between carbon and hydrogen? We know that there's an electron here and an electron here. One of those from each atom that shares into a bond that has 2 electrons. So that's also considered an electron pair. Okay, so that means bonds will spread themselves as far as they can. Lone pairs will spread themselves as far as they can. That's what we're looking at here in this valence-shell electron-pair repulsion theory. These groups of electrons will start to spread themselves as far as they can to give themselves the most space. Okay, so here's kind of a book definition of what I've just talked about. So go ahead and pause the video to get it written down to kind of understand what this is talking about here. Okay, so again, very simply, electrons repel each other. They want to be spaced as far apart as they can from each other. The exception to this is when there's a double or a triple bond between two atoms, right? Those things have to be, those things remain close to each other. A double bond, those two sets of electrons remain close to each other. And in a triple bond, those three sets of electrons remain close to each other. That's the exception there. Okay? So we talked about what electron domain was just a little bit, but we've got two different types of electron domains. Okay, remember a domain is something that's surrounding the central atom. So we have bonding domains. That's any sort of space that contains a bond. And we have non-bonding domains, which contains a lone pair. Okay, so we have two types of electron domains, bonding domains and non-bonding domains. So anything that contains an electron, contains a bond is considered a bonding domain. Anything that contains a lone pair is considered a non-bonding domain. So I'm going to go ahead and draw the Lewis structure here of water. Actually, I don't want to do water quite yet. Okay, a CH4 molecule. This molecule has how many domains? We have 4 domains because 4 things are surrounding the central atom. All 4 of these domains are considered bonding domains because they contain a bond. Okay, we're looking at how many different atoms are attached or how many different things are surrounding the central atom. Just because they're all hydrogen atoms does not mean we have one type of electron domain. We have 4 domains. Each of those domains contains a bond to a hydrogen atom. Okay, so now when we draw the Lewis structures, we should be good at drawing Lewis structures by now. When we draw a Lewis structure, we need to be able to determine how many of these domains a molecule has, number 1, and how many of each type they have. Okay, figure out how many total domains they have, how many are bonding, and how many are non-bonding. Because that's going to help us with our VSEPR theory, this theory right here, to determine its 3-dimensional shape. Okay, so now I need you to find in your notes, in your handouts, I've given you that says molecular geometries or shapes predicted by VSEPR, and you need to get that handout out right now, okay? And it looks like this. Okay, on one side of it is this document, on the other side of it is the electronegativity scale. Okay, so you should have that handout with you. If you don't, you need to get another one right now because you need to have this handout and you'll need it often during this chapter. All right, so now that you've gotten that table out, I want you to kind of take a look at what it means and what this whole sheet is telling us. Okay, so what I would like for you to do is take a look at the headers on each of these columns and rows, okay? This tells us, first of all, this column right here tells us we're looking at the total number of electron domains. Okay, so if a molecule has 4 total electron domains, total, we're going to take a look at these possible shapes for that molecule, okay? Then, from there, we're going to take a look at how many lone pairs does it have. Okay, and when we talk about lone pairs and domains, we're talking about on the central atom only. Okay, we're not talking about lone pairs on outside atoms. We're talking about looking at the central atom. Okay, because this shape is depicted around the central atom. So let's say that an object has, Let's say that an object has 4 total domains and 1 lone pair. Okay, we're going to slide over because it has 1 lone pair. 4 total domains. It would have a shape we call trigonal pyramid. Okay, or trigonal pyramidal, sometimes you'll hear me say. Okay, and it's shaped like a pyramid on the bottom, and it's got 1 lone pair on the top. Okay, this angle right here that corresponds with that tells us that basically each of these domains Each of these electron domains is 109.5 degrees apart from each other. That's the maximum space that something can have in this three-dimensional shape. Okay, so according to these domains, these three bonding domains and one non-bonding domain, this is the best possible arrangement of atoms and arrangement of electrons to give each of those electron pairs the most space. Okay, so go ahead and just take a couple seconds to look over this sheet, get kind of an understanding of what's happening here, and then we're going to do some practice. All right, so let's go ahead and take a look at a water molecule here. Okay, I've gone ahead and drawn the Lewis structure for water for you. And let's take a look at the total number of electron domains. Okay, total number of electron domains on our central atom. First of all, we know that our central atom is, of course, oxygen. Okay, hydrogen can never be a central atom, so it has to be oxygen. And the total number of electron domains we have is 1, 2, 3, and 4. Okay, we have 4 total electron domains. Lone pairs get its own domain. Bonds get their own domain unless they are a double bond or a triple bond. Okay, if we would have a double bond, I know this isn't the correct Lewis structure, but if I would for some reason have a double bond here, this would still only count as 1 electron domain. Okay, but for this molecule we have 4 domains. Okay, so 4 total domains on the central atom. How many of these domains are bonding domains? Okay, you should be able to answer this yourself, but we have 2 bonding domains and we have 2 non-bonding domains. So we have 2 and 2. Okay, so what I want you to do is find the molecular geometry of this water molecule. Okay, so I want you to take your sheet, look at how many total number of electron domains we have for water. We have 4 total domains. We have 2 lone pairs. That means the molecular geometry of our water molecule is called bent. Okay, it has a bent molecular geometry. So that means between each of these electron domains, there are 109.5 degrees of separation between each of those electron domains. Okay, so the molecular geometry of water is bent. All right, let's try a couple more now. What's the Lewis structure for the compound BCl3? First of all, I want you to just see if you can name this molecule. Get a little extra practice in naming the molecule, just for fun. Okay, the name of this molecule, first of all, we should have gotten as boron trichloride. Okay, and the Lewis structure for this molecule, hopefully you've started to do this on your own. Boron has 3 valence electrons. Chlorine each has 7, which means total we have 24 valence electrons we need to represent in our Lewis structure. So we're going to draw our skeleton, and then we can fill in our electrons along the outside. Okay? After we draw our skeleton, we've used 2, 4, 6 electrons, which leaves us with 18. So we can fill 2, 4, 6, 2, 4, 6, 2, 4, 6. Okay, so if you have a question here about boron, boron has 3 valence electrons to give up, right? To start with, it's got 3 valence electrons, and we've used each of those 3 within a bond. Okay, boron started with 3 valence electrons available to bond, and we used all 3 of them. So boron is a molecule that we consider to be able to have an incomplete octet. Okay, so boron is one of the few molecules that can have what we consider an incomplete octet, which means we don't have to fill an octet for boron. Okay, it's okay with having only 3 bonds. Okay, because it only has 3 electrons to give up anyway, and it doesn't like to take on a charge. So boron is one we consider okay to have an incomplete octet. All right, so we're good with this Lewis structure right here. We've used all of our electrons. Chlorine likes to have 3 lone pairs and 1 bond, which is what all of these chlorine atoms have. Okay, so we've got now our Lewis structure for boron trichloride. Now I want you to use your molecular geometry sheet to determine what the molecular geometry is of this molecule. The first thing that we need to determine here is how many electron domains do we have total? And hopefully you've answered this question already, but we have 3 total domains. Okay, so we can start taking a look on our molecular geometry sheet to 3. That means we've either got the option of trigonal planar or bent. We've got 2 options there. How many of these 3 domains are bonding domains? Okay, they are all 3 bonding domains, which means we've got 3 electron domains, no lone pairs, which means our molecular geometry is called trigonal planar. Okay, and you can envision this as being a flat plane, a flat little triangle. It's not really even 3-dimensional here. It's a flat triangle. Okay, it's planar, which means flat, and it's a triangle. Trigonal planar. There's no 3-dimensional aspect to this one, really. It's planar. They're spread as far as they can. They're each 120 degrees apart. Each of those chlorine atoms are 120 degrees apart. So my drawing isn't exactly accurate for 3-dimensional, but it's close enough. All right, so we're going to try a couple more here. Find the molecular geometry of CBr4. First thing that you need to do to start solving for molecular geometry, you've got to draw the Lewis structure. So if you want to pause the video now and try to draw the Lewis structure yourself, and then unpause it and see what I get, that would be a great idea. Okay, so here's our Lewis structure for carbon tetrabromide. Carbon tetrabromide. That's the name of our molecule here, CBr4. Carbon has a full octet, 2, 4, 6, 8. Each bromine molecule has a full octet. Remember, halogens like to have 3 lone pairs and 1 bond. All halogens like to have 3 lone pairs and 1 bond. So bromines are all happy. So here's our Lewis structure. Total number of electron domains on carbon, which is the central atom. 4 total domains. And how many of those domains are bonding? We have 4 bonding and 0 non-bonding, or 0 lone pairs. All right, so let's take a look at your molecular geometry sheet. If you go to 4 electron domains, no lone pairs, we have one we call tetrahedral. Tetrahedral. Okay, this is a super common molecular geometry. Okay, for pretty much anything that has 4 different atoms bonded to it and no lone pairs, we've got a tetrahedral atom. Okay, and so this tetrahedral is kind of a pyramid shape on the bottom and 1 atom sticking up on the top. And next class we're going to do some extensive practice with looking at these three-dimensional models and three-dimensional things, so you're going to get a little bit better idea of the picture itself three-dimensionally. So next class we are going to work on our Chromebooks, and we're going to be able to manipulate these molecules, view them three-dimensionally, so that you have a little bit better idea of what these shapes really look like in real life. But going back to carbon tetrabromide, we've got a tetrahedral molecule. Okay, 4 total domains, no lone pairs, tetrahedral. Okay. Let's go ahead and look at our next molecule here, CH2Cl2. Okay, it looks a little bit more complex than what it really is. Let's determine which should be our central atom from these choices here, carbon, hydrogen, or chlorine. Which should be our central atom here? Carbon should be our central atom when we draw our Lewis structure. Okay, so I'm going to go ahead and draw the skeleton. C, H, Cl, Cl. It doesn't really matter what orientation you draw these 4 atoms in. We could have both of our Cl's here, both of our hydrogens here, or vice versa, but that's just how I chose to draw it. And then next we bond to each of those from our skeleton. Okay, so let's figure out our number of electrons first. I should have done that first. Carbon has 4. Hydrogen is going to have a total of 2. Okay, hydrogen has 1 each, and there's 2 hydrogen atoms. Chlorine has 7 each, and there's 2 chlorine atoms. So 4 plus 2 plus 14 gives us 20 electrons. Okay, we've used up 8 from just the bonding alone, which means we've got 12 left to use. Does hydrogen get any lone pairs? No. Hopefully you answered no there. Hydrogen gets no other lone pairs. It only has 1 valence electron, so it doesn't have a full octet, right? It only has 1 available, so that's all that it uses. So we'll fill in chlorine with 6, and we'll fill in our other chlorine molecule with 6. Okay, and that means we're done. Our carbon has a full octet, chlorine has a full octet, chlorine has a full octet. Hydrogens are both happy with 1 bond. Okay, so we can take a look at this molecule again. How many total domains do we have? We have 4 total. How many lone pairs? Which means our molecular geometry should be tetrahedral. Okay, for carbon, it's very, very, very common to have a tetrahedral molecular geometry because carbon likes to have 4 bonds. Carbon does not like to have lone pairs when it's the central atom. It likes to have 4 bonds. So whenever carbon's the central atom, it can be a pretty good guess that you'll have a tetrahedral molecular geometry. That's not set in stone, that's not a for sure rule, but it's pretty common. Alright, so the last 2 examples we've done have been with no lone pairs on our central atom. So now we're going to shift and take on a couple examples that have lone pairs on our central atom. So if we've got a lone pair on our central atom, what type of bonding domain is that called? Okay, it's called a non-bonding domain. Right, it's got an electron or a lone pair in it. Non-bonding domain. So we're going to look at a few examples that have non-bonding domains. Okay, so let's go ahead and look at the Lewis structure for NH3. And this is not ammonia because it doesn't have a charge. Okay, we're just looking at NH3. So NH3, nitrogen has 5 valence electrons. Hydrogen has 1, and there's 3 of those, which means total we've got to use 8 valence electrons. So let's start with our skeleton here. We know nitrogen is going to be the central atom because hydrogen is never the central atom. Okay, so I've drawn my skeleton and my bonds. I've used 6 electrons and I have 2 left. So where do I need to put those 2 extra electrons? They go on the nitrogen. Okay, we don't add electrons to hydrogen ever. We add them to our central atom last. So we're going to look here. Does nitrogen have a full octet? 2, 4, 6, 8. Yes, it does. It used 1, 2, 3, 4, 5 of its valence electrons. That's what we like to see. Okay, so I want you to go ahead and determine the molecular geometry of this NH3 molecule. How many total bonding domains does it have? It has 1, 2, 3, and 4 total. So 4 total, and it has 1 lone pair, or 1 non-bonding domain. So if we take a look at our molecular geometry sheet, we've got 4 total electron domains. We're going down the left-hand side, 4 total. Slide to the right until you reach 1 lone pair, which is called trigonal pyramid. Okay, trigonal pyramid, and we've got a pyramid shape on the bottom between those 3 molecules. The lone pair is pulling that central atom upward to make that pyramid. Okay, and again, next time we're going to look at, you're going to be able to see these molecules moving in space, and you're going to get a better idea of each of those shapes. Okay? All right. So when we're talking about lone pairs around the central atom, we want to make sure that we understand the pair, the lone pair, surround these central atoms, and they occupy space just like a bond does. Okay, this lone pair wants to occupy space just like a bond. Okay, so this lone pair wants to be spaced out from other lone pairs or from other bonds, just like everything else. But it's really important for you to understand that lone pairs still act as pairs. Okay, within a lone pair, those 2 electrons are not repulsed by each other. They have what we call opposite spin states. Okay, and we might be able to remember back a little bit when we talked about quantum numbers and we talked about spin states. But those electrons are not repulsed by each other. They are still okay with being together in that orbital, right? They want to stay together within that pair, but then they're repulsed by other pairs, okay? So when we have a lone pair, those 2 still have to stick together, but they want to be spaced out from other lone pairs or other bonds. Okay, so now we're going to look at what it means when we have a double bond. And I mentioned this just briefly, but what happens if we've got a double bond or a triple bond? How many domains does that count as? Okay, and the answer is that when you have multiple bonds leading from one atom to another, it only counts as a single bonding domain. Okay, it counts as 1 bonding domain. So even if we've got a double bond or a triple bond, it's still only leading to one other atom, which means it's 1 type of domain. Okay, so I want to try to use VSEPR theory to predict the shape of a molecule of carbon dioxide. So you've got to know what carbon dioxide is first. CO2. And let's go ahead and try and determine this shape of a molecule of carbon dioxide. All right, so to start with our Lewis structure here, we know carbon has 4 electrons, oxygen has 6, and we've got 2 of them. So we've got 16 electrons that we need to represent. We've got 16 total electrons we have to represent here. Which of these atoms should be the central atom here? It should be carbon. Hopefully you answered that. And so we've got our skeleton drawn, and we'll start with a bond each way. Okay? So far we've used 4 electrons, and we've got 12 left to go. So if we start filling in our molecule here, we've used 6, which leaves us with 6. And we used all 6 here, which leaves us with 0. So we've used all of our electrons. Now we can go back to see, does each of these have a fulfilled octet? Oxygen does. Oxygen does. Carbon does not, which does not make carbon happy. Okay, carbon likes to have 4 bonds and no lone pairs. Okay, so the way that we fix that is we're going to move a lone pair into the double bond for both sides. Okay, now let's go ahead and start over our count here. We need to use a total of 16 electrons. So we've used 2, 4, 6, 8. Leaves us with 8 left. To fulfill oxygen's octet, we give it 2, 4, which leaves us with 4. Same on the other oxygen, we give it 2 lone pairs, which leaves us with 0 electrons. This is the correct Lewis structure for a CO2 molecule. Okay? Although this top one looks like we've used all of our electrons, it's not correct because carbon does not have a full octet. Okay, here we've got full octets all around. So oxygen is using 2, 4, 6, 8 electrons. Carbon's using 2, 4, 6, 8. Other oxygen's using 2, 4, 6, 8 electrons. Okay? So now if we look at Vesper theory to determine our molecular geometry, we've got how many total bonding domains? Okay, hopefully you're answering 2 bonding domains. We have 1 here and 1 here. 2 total. And 0 lone pairs. So if you travel on your sheet to 2 electron domains, the only option is to have no lone pairs, which means our shape is linear. Okay, each of these oxygen atoms are 180 degrees apart. It's a linear, it's a straight line of molecules. So to recap there, if we've got a double bond or a triple bond, it still counts as a single domain because it's leading to one atom. Okay? And when we're looking at lone pairs, it's important we don't count the lone pairs on outside atoms. We're looking only at the central atom. So carbon here is our central atom. It's got 2 bonding domains, no lone pairs, which gives us a linear geometry. Okay, I want to try these last 2 on your own. Okay, try these last 2 on your own. So you need to start with the Lewis structure and then give me the geometry for both of these. So I want you to pause the video now and start working these out, and I will give you the final answers here in just a second. Something I want to point out with this first example is that you'll notice that arsenic has 5 things bonded to it. It's got 5 domains, which means it's more than an octet. Okay? It's bonded to more than 4 things, which gives it 10 total electrons, and that is okay. Okay? Some of these elements, when we get down into period 4, period 5, period 6, period 7, we can start to have some things that we call expanded octets, and arsenic is an example of that. Okay, so we can have these things that are bonded to more than 4 or that have more than an octet, and that's okay. These are always covalent molecules that work out that way, but it's okay if it's got an expanded octet, so just draw that Lewis structure as it's written. All right, so in our second example, again, carbon has 4 bonds and no lone pairs, which is the tetrahedral molecular geometry. It's another example with carbon as the central atom is most of the time tetrahedral. Again, that's not something that you can consider a rule. It doesn't always work like that, but for the most part, it really does, okay, unless carbon has double bonds or triple bonds with it, okay? So that is it for molecular geometry. We're going to do some practice now.